This is going to be an extremely brief video on this idea we call translation in terms of geometric translation of, say, some figure in our coordinate plane. You know, of course, again and again in these series of videos I talk about how we're going to spend a lot of time looking at graph theory, at least in my classes. You know, how we can affect graphs. But let's take a look at, say, like a sample graph here real quick. What if we had, say, a graph that we deal with often enough? Whoops, I forgot to click on OK. Let's go back to pink here. But how about, like, say, a cubic function here? And, you know, I know this is a kind of a lousy cubic function, but you got to realize this is an infinitely many xy coordinate points or solution points to a variable relationship. But what would necessarily happen, let's say, if we explored, if we translated this, which is, you know, kind of a technical math term for essentially just pick it up and shift it left or right, up and down, you know, in the rectangular coordinate plane, and what implications does this have in terms of an algebraic representation of, say, a rule that is associated with this given function. But essentially what we want to be doing here is we want to be sliding things up and over. But imagine if I wanted to slide this, say, 2 units to the right and 1 up. What I'd necessarily be doing is grabbing every single point on this graph and sliding it over 2 and up 1, over 2 and up 1. And I could do this infinitely many times, but what we're really looking for now is this new graph. And so we spend so much time you know, graphing things that it's kind of convenient to, instead of learning how to graph every single rule in a new way, how about we do this? Why don't we just memorize what we'll call, say, a library of functions, like this very basic cubic graph. And instead of learning how to graph every other cubic, what we'll essentially do is look at it in the sense that what we're really taking is the original cubic graph, this idea of the cubic graph in the most basic sense, trivial sense, and kind of altering it such that it looks like this new, say, cubic graph. We could call this an entirely different function, but at least, you know, all we say is this new function in blue is only, you know, an alteration of the original. So when we want to define this, you know, we look at this geometrically, and we do this quite often. We want to define this quite often algebraically. So here's how we're going to go about this. We're going to take a look at this and we say, okay, just real simple. You know, we say, given some point xy on this graph, and I don't care which one you choose, we say, okay, if I were to shift all, you know, my graph 2 over and 1 up, I'd be shifting every single point 2 over and 1 up. And you know, kind of graphically, we'll look at it, or algebraically, excuse me, we'll look at it this way. We're going to say translation is kind of represented thusly, okay? So we say translation. We say, all right, we'll give every point that has been translated from the original as x plus some h value and y plus some k value. I'm going to go ahead and kind of point these out and show you the steps before I show you the dance here. But we say h, and I've always kind of thought of this as h for horizontal. You know, who knows though? A lot of people do math and they don't speak English. So horizontal, this really represents horizontal translation. It's good to write down kind of dynamic notes here, show it here. And this represents vertical translation. But essentially, there we go, I got a picture in there. We use K probably because it comes after H and is not necessarily a J. But really all we need to do is, if we're taking every point, and say in this specific example up here, and we're shifting it 2 to the right and 1 up, what we're really doing is adding, you know, in this case 2 to every x value in the xy coordinate plane, adding 1 to every y value in the xy coordinate plane. But in general, we say we're subtracting h from every x value and k from every y value, and really the new point would just be whatever x and y were originally altered by, you know, this h and this k on the x and y respectively. So we're going to kind of point things out as vertical and horizontal translation, not respectively here, but as x plus h and y plus k, where h is always horizontal translation and you know, k is always vertical. And I know you're like, this is so easy, and I'm like, you're right, this is easy. But I do want you to get used to this idea, this notion of h and k being horizontal and vertical shift. You know, and just to kind of, you know, show this real quick, what if we had a few points here? We'll go some really, really simple ones here. How about 0, 1, 0, 1? And we'll even go, how about 0, 4, 0, 4, and another point we'll call this 2, 1. We'll, you know, maybe be looking at a triangle in a geometric sense here, or maybe we could have a function, but we're going with the triangle. But if I wanted this new triangle to, say, translate 3 to the right for the sake of convenience on this problem. 3 to the right and 1 up. What I'm necessarily going to do is I'm going to take all the original x values and I'm going to add 3 to them. Whoops, I'm going to write that there. And I'm going to take all the y values and I'm going to add 1 to them. But essentially what we're saying here is h again is this horizontal shift and k is this vertical shift. A good geometric review here. So we say, okay, so how about we'll switch over to like a green. Why not? We don't go green often. But if we said x plus 3, you know, insert x value here. So looking at this first one here, we say x is 0. We say 0 plus 3 would be this new x value. So we say 3. So we say 1, 2, 3. Or pardon me, we say x plus 3. This would be 3, and then y, which is 1, plus 1 would be 2. So now what we've got here is over 3 up 2, essentially. And so you'll see here we just bumped this over 3 and up 2. And we'll go ahead and proceed and do this with the rest of them. You know, I can kind of stretch this out here. We say 4, 5, and 5, 6, 7. Sorry to stretch this, but we say, okay, how about this point here? 0, comma 4. We'll add 3 to the x value, which was 0. 0 plus 3 is 3, and 4 plus this 1 here is 5. So we say 3, comma 5 here. And that would be, whoops, this new x value, 3, comma 5, and it's not a very good drawing. So I apologize for that. Oh, that's because this one's off. This should be here, not there. And we say, okay, so now this last value, 2 plus 3 is 5, and 1 plus 1 is 2, so we say 5, 2. 5, 2 would essentially be right here. And all you're going to see is we basically translated this. But again, keep in mind, we're only doing this because we can take a library of functions, say, you know, this function right here, and say, I just want to shift it. And we say, okay, let's take all the points, shift them. And, you know, often we might even use vector notation to represent that. But it's a good, you know, kind of notation to be aware of.